Oh yeah, I'm excited too, buddy. Oh hey, I'm just really excited because I just figured out a new weight loss program. See, all I have to do is this. And I lose between 5 and 10 grams or so. I calculated it with the ideal gas equation. See, the air in my lungs has mass, and so when I breathe it out, I lose weight. And if I just do that like 65 times in a row, I'll lose a pound. Here, let's try it. I'll count them. Well, hello everybody. Welcome back. If you were just watching our video on gas laws, today we're going to discuss this further, and we're going to talk about the ideal gas law, which sounds like it's some sort of fancy bragging of the equation. What really means is that it's valid under ideal conditions. If you don't remember what ideal conditions are, go back and watch the video on gas laws, where we discussed that if you're not really crowding molecules and draining the energy out of them, then their self-volume and their interaction can be ignored, and you'd have a very accurate result with any of the gas laws. Now, remember, you don't have to memorize equations if you just remember, or if you're always given the value of the gas constant. There it is in units of pressure, volume, moles, temperature. That is PV over NT. And we give it the symbol R. Now, we don't usually express the ideal gas law in the form of a fraction like above, because 7/8 of people don't like fractions. And so, actually, I think it's more like 8/7. But this ideal gas law is usually quoted PV equals nRT, where P is pressure. Now, when you're dealing with these problems, the units matter. Unlike last time, you'll notice that we had pressure could have been in PSI, millimeters of mercury. Here, the units of pressure, volume, temperature, of course, has got to be Kelvin. But pressure and volume must match the value in your gas constant. So we're a little picky with units here, but this is much more versatile. And let's waste no time. Let's do some practice. Whoop! Practice. Whoop! So here's a typical kind of ideal gas law equation. So calculate the mass of, okay, what's mass? Grams. Right? So of a deep breath of air, this is going to prove or disprove my weight loss theory. Assuming the average lung capacity of a human is 6.0 liters V. I'm going to go label these things as I go along. Body temperature is 37 degrees T. And you know what I'm going to do, folks? I am going to, before I forget, I'm going to go and convert that to Kelvin. All your temperatures have to be in Kelvin. 37 plus 273 is 310. Remember that. Just like when we were talking about gas laws. And a pressure of 750 millimeters of mercury. Now, the first thing you can do is also say, every time I'm given something like this, I always have at the ready the unit, the gas constant, 0.0821 liters times atmospheres per mole per Kelvin. There's my Kelvin, there's my liters. Oops, I've got to change the units of my pressure to match that of the gas constant, which is atmosphere. So it turns out that there's 760 millimeters of mercury in an atmosphere. So unlike last time, you have a little bit of prep work to do before we can plug it in to the equation. So there's 760 millimeters of mercury in an atmosphere, and we got a little bit less than 1 atmosphere. So 750 divided by 760, 750 divided by 760 is 0.9868. Now we'll trim digits at the end. Now, you'll notice that this has a different form, these kinds of problems, than when they gave you 2 pressures and they said, hey, this pressure is going to change and it's going to become that, and yada yada. You'll notice that you just get 1 value of pressure, and if you have 4 of the 5 variables, actually this isn't a variable, R, you always have R. That's like free space in bingo. But if you have 3 of the 4 remaining, P, V, N, or T, then you can go ahead and you just solve for what's missing. Now I can tell you right now, I have P, I have V, I've got T. What's missing? Moles, right? And you could go ahead and remind yourself, in case you're worried, you know, just say, okay, I always got P, V equals nRT. Take inventory of what you got. Right? I'm going to go through and I'm going to take inventory of what they gave us in the text of the problem. They gave us a P. They gave us a V. They gave us a T. We always have R. I don't even have to know what I'm doing yet. And I could just say, well, I know that next step is I got to solve for N. And then what do you know? N is going to give us our answer, because N can be converted to grams, as we know from many times over. So I'm just going to go here and solve for N by dividing both sides by RT. So N equals PV over RT. And I'm going to stick numbers in. And if I don't get units of moles because maybe my pressure wasn't converted correctly or whatever, then it'll stick out at me like really obviously. So 0.9868 atmospheres. And don't fall under the spell of trying to fast track this. Put your units in. Units always go with each number. So 6.0 liters. And the reason that is very valuable is because now down here below, while I write liters times atmospheres per mole per Kelvin, and then 310 Kelvin. If I did this right, all my units except what they asked for should cancel. Let's check ourselves before we wreck ourselves. Bang. Atmospheres cancel. Liters cancel, because liters in the numerator, liters in the denominator. And my units of Kelvin, although they're in the denominator, cancel. I get 1 over moles, which is moles. So the answer here, actually it's not the answer yet now, is it? We're 1 step away from the answer because they didn't ask about moles. 0.9868 times 6 divided by 0.0821, and then divide that by 310 is 0.2326 moles. Of what? Air. Okay? And so, you know, what we got going on here is that's just moles. They want grams. Luckily, they gave us the grams per mole. Now, why is that 28.9? You'd be like, hey, I don't see that on the periodic table. Remember, air is a mixture. So it's about 21% oxygen, which is 32 grams per mole, and it's about 79% nitrogen. We'll even ignore the argon, because you'll see we only got like 2 sig figs in this whole thing. And so, you know, you could say that it's about, weighted average wise, about 3/4 of the way between 28, which is nitrogen, and 32, which is oxygen. So you know, 1 mole air, 28.9 grams of air. And that's our last step. And then we'll have our answer, and then the only thing left to do, of course, is to round our sig figs. What did I have? Well, let's get our number first, okay? So 0.2326 times 28.9 is 6.722 grams, 2214 grams of air. Now I got to have a conscience about my sig figs. The least number of digits given was 2 with my volume, so I'm going to just call my answer 6.7 grams. And that's how much mass you gain if you take a deep breath. You know, given that your lung capacity is exactly 6 liters, you know, that's an average. And when you breathe out, you lose that much mass. Of course, you can't breathe out 65 times in a row without breathing back in. That's what I found out earlier. So here's a little concept map of where we are in Gen Chem 1. We got this thing in the middle called moles. We know that that's the key to the solution for every single problem we encounter. And now we've got all sorts of different ways to get back and forth between moles and different things. So here, of course, you go to the periodic table and you see what the molar mass is, and that'll get you back and forth. Grams per mole, moles per gram, and that solves your problem for us. When we have a solution, we usually express it in molarity, capital letter M. That's moles per liter. Or if you remember, you know, M, moles equals molarity times volume if it's in liters. Now what we've got is we've got our friend PV equals nRT, which can get us back and forth between moles if it's a gas. So you have different ways to approach the problem depending on what the starting material is. Is it a pure solid? Or for that matter, if it's a liquid and you had the density of it, is it a solution? Is it a gas? Either way, we can get in and out of Moleville to solve our problems, like the one we're going to do next. All right, let's apply this now to a chemical reaction. Oh boy, let's just drink that one in. Look at all those words. Okay, now first of all, interesting thing, most of you have airbags in your car, and I, first of all, don't like the term airbag. It's not an airbag. It is a nitrogen bag. I want to start a movement. Nitrogen bag, not an airbag. And so the reason is, a lot of the designs of airbags have an explosive compound called sodium azide. That's the azide ion, N3-, it's a polyatomic ion. And if you zap it with enough voltage, which by the way is what happens when you hit something with enough force, there's a sensor in your bumper basically that shoots a signal to the battery of your car, and all that energy gets shunted into the airbag, which which deploys the nitrogen bag by producing a decomposition reaction that makes nitrogen. And sodium stays in there, but it's not a gas. So this gas will then go and fill the nitrogen bag that deploys in your steering wheel column thingy or in your curtain bags on the side of your car. And I hope you never experience that, ever. But it's a really magnificent invention because nitrogen won't feed a fire. It's pretty inert. If you made this out of oxygen or hydrogen, it'd be a disaster. Okay, so what mass, hey, here we are in grams, of NaN3 would be required. So you know what? I don't know, this is our answer, but I have a feeling that's coming for moles. So to produce enough, there's V, enough nitrogen to fill V, 45 liters, at T, 298 Kelvin. Switch that into Kelvin immediately. So now I got P, I got V, I've got T. This is very much like the last one. I got P. As a matter of fact, let's go ahead and write down PV equals nRT. R equals 0.0821 liters times atmospheres per mole per Kelvin. You can write that down all the time. Let's go ahead and notice that, yeah, they gave us our volume in liters. They gave us our temperature in Kelvin. Once again, this pressure is not in units of atmospheres. So what I'm going to do is convert it. 825 millimeters of mercury. There's 760 millimeters of mercury, 1 atmosphere. So let's see what that is. And then I'm going to go ahead and take inventory of what I got. And I got a P, a V, and a T. And that means that I can go ahead and solve for what's missing, which to me is going to be moles. All right, 1.0855 atmospheres. There's my P. There's my T. There's my V. And so what do I got? Once again, take your time, take inventory. I got P, I got V, I got R. The universe gave me R and T. So I'm going to go ahead and do the next logical thing, which is to solve for N by dividing both sides by RT, and then we're going to plug it in. It's very much like the last example, except this one has a twist, so don't get bored yet. So 45 liters was given. 0.0821 liters times atmospheres per mole per Kelvin times 298 Kelvin. You know, don't hurry too fast. Check yourself before you wreck yourself. Atmospheres cancel. That makes sure you have it all set up. Liters cancel and Kelvin cancel. This is going to be in units of moles when we get that number. But after that, we got to see, are we actually answering the question? 1.0855 times 45 divided by 0.0821 and then divide that by 298. So 1.996, okay, 1.9966 moles. We'll trim digits at the end. Uh-oh, here's the thing. What's it moles of? Well, this applies to the gas. This is actually moles of the thing produced, which is nitrogen. Now, the mistake would be that I see quite often is someone would say, oh, that's moles of this, and then I go and convert that. Nope, nope, nope. We actually got an additional step here. This is moles of nitrogen. Then we need to go back to good old stoichiometry and convert moles to other moles. So that's the product. Moles N2, moles NaN3. And now, once again, like with stoichiometry, don't think too hard. All that happens is you pick up the number that's right next to that thing that you're talking about moles of, the coefficient, you just pick that up, and it's next to N2 in the reaction, and goes down next to N2 here, 3. And then you take the coefficient that's next to NaN3, and you put it right there. So I multiplied by 2/3. But I didn't have to really think about it too much. And then what happens is, that's moles. The problem is asking for grams, but let's go ahead and just take a little break after this. So times 2, and then divided by 3 is 1.331 moles of NaN3, sodium azide. 1.331 moles NaN3. They want grams. So we got to go look at the good old values in the periodic table, right? Well, I know that nitrogens are 14.01 apiece. Go get your periodic table or look at it. So the nitrogens alone are 42.03. Sodiums are 22.99. So this is 65.02 grams per mole. 1 mole, 65.02 grams. So then times 1.331. So 86.54 162 grams is what my calculator says. Now my calculator doesn't have a conscience about sig figs. Let's see. 3 digits, 3 digits, 3 digits. I'm going to go ahead and say that number is good to 3 digits. That means 86.5 grams is my answer. Now think about how important of an engineering problem that is. If you don't have enough of this stuff, you're not going to properly inflate the nitrogen bag. And if you have too much of it, you're going to overinflate the nitrogen bag. And both of those would be bad news. And so some engineer, and you folks might work on problems very similar to this someday, had to figure out what amount of starting material would produce 1.33 moles, or whatever, 86.5, 1.996 moles of nitrogen, and back calculate how much that was. Go practice, folks. This is good stuff. And, you know, the more you become familiar with the ideal gas law and the gas laws, the more you realize this is really pretty easy stuff. The units practically set everything up and guide you through. Take care, folks. Ciao.